Welcome, everyone. Welcome to the Aaron Biddle Show, a show where we look at this exciting new database for accounting called Changeable, which is implemented in Zig, which comes with a deterministic randomized simulator, which doesn't allocate memory and which is cool in a myriad of different ways. And we try to understand how exactly it works. At the lowest level of detail, we don't do a lot of, well, we do a lot of hand waving at this show, but after every hand waving, we actually go right in the source code and try to get to the bottom of it, how things work. Okay, let's get started. And the topic of today's episode is the changeable nature of persistent data structures. This sounds cryptic, and before we get to that, let's start with the homework I had since the last time. So last time someone asked me in the Twitch comments, like, what is the semantics of inline keyword in Zig, and why would you use that? And my answer was that inline in Zig, as in pretty much every other language which uses inline keyword, isn't actually a hint to the compiler to inline the code, to do the inlining optimization, because inlining optimization is something that compiler just does by default, and you don't really need to hint to it about it. More often than not, you actually want to tell the compiler, hey, compiler, please do not inline this function. I don't want this to be inline because, well, inlining is default behavior. What inlining in Zig does is that it changes the semantics of a function. It makes the call analyzed in a way where if the arguments are known at comp time, then they are also comp time known in the body, which is correct definition of what inlining in Zig does, but there was one legitimate question, like, well, why do you need it? So let's figure it out. Let's try to write some example code, which might or might not work because I haven't tried this before. Again, this is something I understand in theory, but in practice I might be wrong. Okay, so let's start with public static void main function, and let's say that we have function foo. Okay, now let's say that we have function f, which requires comp time parameter t, which is like u32, and this function does nothing. And then we have function share, which takes u32 and returns u32. And oh dear, my stream is interrupted again, which is actually surprising because we did have a stint of stream interruptions a couple of months before, and that was due to Portugal, so we switched our country to Sweden, and the internet in Sweden is much better, but well, apparently something's wrong here still. Let me try to restart the stream then. Again, for folks who are watching this in recorded on YouTube, sorry that you have to bear all this unnecessary fluff. Again, if I had more time, I would have probably made this a blog post rather than, a stream. Okay, so and let's say we have code like this. Let's Zig, not Rust. Let x equals j92, and let's call function f. So this shouldn't compile, I think. So yeah, this fails to compile. Why is that? Well, because here in function f we require that parameter t is known at comp time. But the thing is, in Zig, the rule is that function call is a boundary where you stop propagating comp timeness of things. So kind of like if we look at the G function, well, it is clear that it's like simple and that the compiler actually can evaluate this at compile time. But when Zig actually analyzes the code, it like conservatively assumes that arbitrary function call might not necessarily be evaluatable at compile time. So here, like, x becomes runtime known, and we get an error here, which makes sense. Now, if we mark this function as inline, then what would happen is that compiler will semantically inline the body of this function. And so when analyzing this code, it would actually know x at comp time and would propagate this information right up to the output of this function, and the x will be also known at compile time. So this should work, I think. Okay, yeah, this compiles nicely. But then the question, well, why do we need an inline here? Well, can we just say this? Because, well, this kind of like does the same thing, and it also is clear semantically, because, well, we see this comp time, we want this thing to be comp time. So, like, why do we need a line here? And that is like the thing is that with inline, you don't have to make all of the arguments comp time. So let's say that what actually happens here is that we have x and we have y. And what we do with y is that we actually go and print this. Okay. And let's say we call this function like this. So I think this shouldn't compile, although I'm not sure if printing to standard error is allowed in debug. Okay, yeah. So you see here, we have two arguments, and if we just we like do something runtime with one of the arguments, and if we try to evaluate the entire call at comp time, well, it fails because, well, you cannot print to standard error at compile time. But if we actually say that this function is inline, then this should work. And okay, now let's see if I did my homework properly. Yes, okay, yeah, I was really nervous here because I kind of like understood this in theory. I haven't checked it. Okay, yeah, it works as I expect. So you see, we kind of like we have like one argument which is runtime known, and well, kind of like here like y is also like compile time known, but we could imagine that we say that hey, okay, const y get y, and get y is just some runtime known function, and we do this. Yeah. So in this picture, you see that like only one argument is comp time known and another argument is non-comp time known, but still the result of this function is comp time known. And I think if you remove this inline but add comp time here, I think this, well, I'm actually not sure if this will compile or not. Yeah. Okay. I don't understand why it fails to compile in this particular way. Well, yeah, okay, yeah, that's yeah, it fails. It actually fails in a way I expected it to. So we mark the argument as comp time, but this actually doesn't tell us that hey, the result is going to be comp time, because from the signature, well, the function might as well return y here. So that is the extra expressivity that is given to you by inline. Well, the question is like, why the heck would you ever need this functionality? And let's look at the example from standard library. Where is standard library? Standard library is in Zig. And we look for inline fn, not in file, in line fn. And there are a bunch of inlines which actually probably should not be inlines, but there is one somewhere, well, yeah, this one. So this one, this one is like actually pretty crucial that it is inline function, because this is exactly the same pattern. We have a function where one argument is runtime, but the rest of the arguments are comp time. And we also want to make sure that the result of this function is comp time. So this result actually doesn't depend on this runtime parameter build. We use build for some side effects during the computation, but we actually don't use it to compute the final value. So that's why, like at the call side, you cannot say just something equals comp time, lazy import, because, well, B is not comp time, but with inline it works. Okay, and I think yeah, this is the same deal. So we have a runtime argument, we have a bunch of comp time arguments, and to make it work correctly, we need to mark this thing as inline. Okay, so with that bit of Zig's trivia covered and out of the way, let's get back to our topic of databases. Okay, so the changeable nature of persistent data structures. What the hell does it mean? Well, let's recap what we've been learning for the past few episodes. Hi, Krugmoon. I cannot answer you in the Twitch chat right now because, well, I am sadly logged out of Twitch, but you can still write your question or whatever, and I will be able to see it. Okay, so we've been discussing Tiger Beetle's data file. So this is the data file. in the data file, we know that it starts with like this mysterious superblock, which we haven't covered yet. So this is mystery. Then we have a write-ahead log. So things that the thing that stores incoming messages for consensus. Write-ahead log. And the rest of the thing, like this here, like the whole rest of the data file, the bulk of it, like the terabytes, is the grid. So the grid is the principal storage of actual data. Like everything here is just some metadata about like required for the function of a database itself. The grid is actual data. So let's zoom into the grid. The grid is, well, it is a grid of blocks, meaning that it is nicely subdivided into equal-sized blocks of half a megabyte each. So, okay, is there some quick way to draw a grid here? Okay, so yeah, looks like a grid. So the atomic element of input-output of Changeable is this block of half a megabyte data. You cannot write a smaller amount than that, and you cannot read a smaller amount of that. What we are using these grid blocks for? We're using these grid blocks for implementing log-structured merge tree. An LSM tree is a sorted set data structure. So let's kind of like put grid on the stack, and let's look at the building block of the LSM tree. This is a table. So what is a table? Table is multiple blocks. So zooming into the table, there is index block, and index block points to the data blocks. So this one is index, this is data, well, let's call it various blocks. These blocks on the right, there are many of them for each table. They just store sorted arrays. They're like literally arrays on disk. The index stores pointers to all the data blocks. The data blocks inside the table are disjoint. So given this table, you can actually look up a value inside it by first doing a binary search in the index block and then doing a binary search in the corresponding value block. Okay, and yeah, these blocks here are exactly those blocks we were discussing in the grid. Okay, now you can take a bunch of tables and arrange them in a so-called level. Again, if you maintain the invariant, and we do maintain this invariant, that the ranges of the tables inside the level are disjoint, then you can binary search this entire level. So you first binary search for the correct index block, then you binary search inside this index block for the correct data block, and then you binary search inside this data block. So this is again kind of like big sorted array, which is comprised of like smaller sorted array, which is ultimately comprised of value blocks which store just plain contiguous arrays of values. This is kind of a static data structure, and the goal of today's lecture is to show how it evolves over time. And this is where like the changeable nature of persistent data structures comes in. Because the data structure we will be describing right now is persistent in two different senses of this word. First, it is persistent as in non-volatile. It is stored on disk. So even if you unplug your computer and then plug it back in and boot it up, the data is still going to be stored on the hard drive, because hard drive is a non-volatile storage. It persists across restarts of the computer. The second sense in which this data structure is persistent is that it is immutable in functional programming sense of the world. So when we will be updating this data structure, rather than updating it in place, we will be doing non-destructive updates. Okay, so how this all works together. Okay, so we have a single layer. One modification we can apply to this data structure is we can say, okay, so if this is state at T1, then at T2, we can take a different layer, well, let's say it's a smaller layer, just 2 tables, and layer it on top. And say that our lookups are hierarchical. So if we want to look up some key, we first look it up in the first layer. And if we found a value, then that's the answer. If we didn't find the value, then we go to the second layer. So this hierarchical lookup nature kind of already gives you this changeability. So rather than changing data structure in place, you could actually just layer more layers on top of it, where new layer specifies just the changed parts, just those things which need to be occluded to provide the semantics of a change. Okay, so I guess now let's take a slight detour here. So kind of when we were discussing LSM tree, we looked at very specifically how this index block are laid out on disk, how the value blocks are laid out on disk. So if you recall, we had this schema file, which basically said us, hey, there's the index block, there's the data block. For these layers, levels, and layers of levels structure, we have in hand waving. So, important thing to notice is that this entire structure of layers is in memory. Okay, this is too small. Okay, let's this says in memory. So all the actual data, all the actual tables are on disk, and in memory we do not maintain pointers to every single data block in the grid, but we do maintain a pointer to every single index block in memory. So that's how lookups work, given this in-memory structure for tables. And I think we also looked at that when we were looking very briefly at the thing called manifest. Okay, yeah. So manifest is that in-memory structure of layers. Using in-memory structure of layers, you can look up the corresponding index table, then the corresponding data table, and look up your value. The question is, well, how do we get the data in memory? So if we have this structure of tables in memory, then that's okay. We can't do operations with this data structure. But what if we just have restarted and we only have the data file? How do we reconstruct this structure of layers and tables in memory? And that is the topic of our today's episode, the manifest log. So no, not the manifest log. Yeah, this one. So this is what we are going to discuss today. How does it work? Okay, it's actually works in a pretty simple way. like how could you represent this data structure on disk? Well, one way you can do this is that you can like literally serialize, like, hey, here is the full set of layers and tables and whatnot we have. But it's actually not the only way to do this. A different way to represent this data structure is to build it incrementally. So see something like this. Okay, let's start with just an empty set of tables. Like there is like 0 tables. And then we have an operation of like add table. And well, this adds table. And then if we have a bunch of these operations, then we have a layer, and then we can add a bunch more at table operations and reconstruct more of the layers until we get to the final data structure. So again, serializing instead of stores the manifest as a sequence of primitive operations, where operation is just add table and remove table. So let's take a look at how this works. And again, well, okay, so this actually, I haven't told you everything I needed to tell you. Okay, so that's like the logical idea. We are going to represent the set of all layers of all the tables of Changeable as a logical log of events which adds tables one by one. So the idea here is when we start, we read this log from disk, and then we like incrementally reconstruct our state in memory. How do we exactly store this on disk? Well, we store this in a sequence of manifest log blocks. And this brings us back to the schema.zip. So manifest log is a sequence of manifest node blocks. And each manifest node block is an array of table info. So let's look at what this table info is. Okay, so okay. The important, let's see. Okay, so first of all, the table info describes the table itself. So the minimum key stored in the table, the maximum key stored in the table, the checksum of the index block, and again, like checksums are always transitive. The index block includes checksums of all the data blocks. So this checksum, in a sense, checksums the entire table, not only the index block. The address of the index block, then the snapshot information, and we'll get to snapshots at some point later. Number of values in this table, the ID of the tree that stores this table. What's tree ID? Well, kind of like right now I'm describing a single LSM tree, so a single sorted set. Obviously, if you can represent a single sorted set, then you might as well represent a bunch of different sorted sets. So each tree is a separate sorted set. And then label. So label is like the critical part here. So this is just table. And then the label says which level this table belongs to and whether this is an inserted, updated, or removed table. So what this means is that this incremental log of events allows us not only to construct the resulting manifest in the append-only manner, but it actually allows us to change the manifest. And well, changing the manifest is exactly what we will be doing during compactions. So to refresh a little bit on what is a compaction. So let's say that we have a bunch of tables at one level, and like a smaller amount of tables. Well, let's just say just one table on a different level. And because the lookup is hierarchical, it might be the case that, for example, we have a symbol, we have like identical key, like, I don't know, 1 here, and we have 1 here. And here, like this one maps to a rhombus, and here this one maps to a circle. And then we also have to here, and to here, and let's say this one maps to a rectangle, and this one maps to a rhombus. So, because our lookups are hierarchical, kind of like this one here and this one here is basically just that data. Like we don't need to store this. For those who just joined, what we are describing is the structure of the log-structured merge tree in the Changeable database. And specifically, while in all the previous episodes, we took a very static look at what is at the data file in a given point in time, in these episodes, we start thinking about how data evolves over time, so how we actually modify the data. And one of the procedures is compaction. So if we take a static view of the LSM tree, we get this hierarchy of layers where earlier layers shadow data, occlude data from the bottom layers. And that creates opportunity for minimization. If one key is shadowed, then we sort of like can delete this whole thing, and we can delete this whole thing. So but again, these are some data blocks on disk, so we cannot actually just delete those blocks. But what we can do is that we can, let's say this also had 0 and also had 3, which we are like, okay, let's say that they both map into X. What we can do is that we can take this whole set of 3 tables from 2 different levels and compact them. So instead of this set, we can say, okay, so let's do this. Let's produce a set of tables which contains only up-to-date values. And then in our tree, let's remove those 3 tables and substitute these new ones. So this is compaction. It doesn't change the logical set of keys that are present in our LSM tree, because compaction only ever reduces the keys which are occluded, which are not reachable from the root of the tree anymore. But it compresses the physical space. Before we had 3, before we had 3 different tables, now we only have 2. So these are new tables. They use different data blocks, but these data blocks here, because they are no longer referenced, they could be considered free. We'll get to how exactly we garbage collect free blocks later, but right now, like this is the idea that you could replace some set of tables across different level with a different subset of tables, which might actually be physically smaller as long as logically the data is the same. But to do that, you actually need this remove and add operations, and that's what is the event field in the label field is for. So again, our manifest log is a sequence of block where each block is a sequence of table infos, and each table info specifies a table by its checksum and address of its index block, and it specifies what are we going to do with this table. We either are going to add it to a particular level, or we're going to or remove it from a particular level. And I'm actually not sure what's an update. Well, I guess update. We use update when we move the table from one level to another. Okay, and from this manifest, we are actually, from this manifest log, from this sequence of block, we're actually going to reconstruct the full manifest. Okay, so let's dive in and see how this looks. Okay, let's start with I need to explain the whole trailer situation. Okay, we'll get there. Not necessarily in this episode, but well, the size of target is finite, so eventually we'll cover everything. Okay, so let's start from the start. Okay, manifest node. Manifest node has metadata, so this is a bit which is some, well, not a bit, it's actually many bits, quite a few bytes actually, which are stored at the beginning of a block, which is different for each block. And the metadata for a manifest node, curiously, includes a checksum and an address of a previous manifest block. So on these manifest log blocks actually form a linked list. So you start from a pointer to the first node, and then you read some amount of events, and then you go to the second node, etc., 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 and eventually you'll reconstruct the entire table. Yeah, apparently we also store like the total number of table info entries in this block. Then previous just gets us the previous node, which is pretty simple. So how do we instruct the metadata? Well, we take the pointer to the block, and we extract metadata by casting the beginning of the block to. So this is a cast. We cast the beginning of the block to the header, and as a reminder, the header is shared between messages which go over the network and blocks which are stored on disk. Then in this header, we take the metadata field, and that's our metadata. Okay, how do we get to the previous block? We fetch metadata, and then we look at these checksum and address fields in the metadata. Pretty simple. If the address and checksum are 0, then there is like null pointer. It means, hey, the linked list ends here. Then we have the size of a block, which is the size in bytes, which is simple, the number of entries multiplied by the header, plus the number of entries multiplied by the size of entry, which is the size of table info. And then we have accessors for actual tables. So again, super simple. We take the block, then we take everything past the header up to the size. So, okay. How do we actually use this? Let's take a look at the manifest log. And I must confess that I actually don't remember where is, I think it is called open. Okay, yeah, this is open function. Function that given the pointer to the very first block of the manifest log, reads the entire manifest block and invokes a callback. And the callback should just take, well, okay. I'm actually curious what happens. Oh, well, right. Okay, this both things are callbacks. So the callback, which is called callback, is what is invoked at the very end of a procedure to signify that, hey, we finished reading the entire manifest log. The open event is fired for every table info so that we can actually react on that and add the corresponding table info to our in-memory data structure, which represents this stack of layer, which is the manifest again. So to be more specific here, if we look at the manifest, we see that the manifest is an array of levels, and we see that a level is a sorted a set of individual tables. So level equals where is const level defined? Where is level defined? Level. Okay, yeah. Why haven't I found it before? Okay, yeah. So level is manifest level type, and a manifest level internally is stores a sorted array of tables. Anyway, yeah. So open event allows us to add this table info to this manifest log. So let's trace the path of the open flow. Okay, so we are opening our manifest. Somehow, so this is explicitly magic. Through some magic unspecified so far, we get the checksum and the address of the latest block of the manifest log on our loose entry. And then we go and say, okay, we are going to read this block. Here we actually store in memory the address and the checksum of this block so that we also know all the blocks of the manifest log. And then we actually go and ask our diagrid, hey, diagrid, please read us this first block of the manifest log. And again, a reminder that this grid read block might actually go and repair this block from some other replica. So this is actually cool. So manifest log is not the actual data. It is the metadata about where are all the tables and whatnot. But exactly the same recovery mechanism is used for corrupted metadata as for corrupted data, because everything is stored in uniformly sized grid blocks. So you only need to implement a repairing procedure 1. You only need to teach your database to repair grid blocks to teach you to repair everything. And again, when I say repair, what I mean is that we ask a different computer to give us block with the same address and the same checksum. Okay. We ask to read the block. After we have fetched the block, we will go through every entry. And what is tables used? Okay, yeah, tables is just, okay, so the table is an entry. If the table is removed, then we just mark, okay, I kind of like hate this z-less behavior which actually moves through type aliases, because, well, if I'm looking at like definition of tables removed, I'm actually I want to find tables removed. Yeah, so this is a hash map of table addresses. Why do we need this? Well, because, like, remember, so this is a log of events, and we look at events from the newest events to the lowest, to the oldest events, and that means that newer events actually shadow old events. So if we had a particular index block on disk, and at time t, we said, hey, this block is removed, then even if at the previous time we were adding this block, we now know that it is garbage. So again, if we remove a table, we no longer need to add this table back because we know that it is removed. Okay. So if we want to remove table, we just mark it here. This table is gone. Otherwise, we want to insert this table. Okay, if you want to insert this table, but it was previously removed, that means that this table now needs to be dead. If we have this table instead of remove tables, then we just do nothing here. Otherwise, we need to say, hey, actually this table is inserted. And we invoke this open event callback. And I won't see how we actually wire this all together, but I think what open. So I want to find the other end of this callback, and I'm not actually. No. I'm not actually finding this. Okay, well let's do this hardly. So we say manifest log open. Okay, we do this in the forest and we pass manifest log open event. Okay. Okay, and that, that goes to the tree. Open table, and we haven't looked at the tree too much, and then the forest anyway. But yeah, okay. So the main thing here is that, like, okay, so when we call this callback, we ended up in this open table function, and what's happening here is that we oh dear. Okay, I always want to tell as little as possible so that we progressively, slowly absorb the whole code base, but sometimes I need to tell you more. So extra detail. As I've said earlier today, we store different trees. And the interesting thing here is that different trees might actually store different types of data. So the sizes of keys and values in different trees are different. They are different compile time types, but we have a single manifest log for all of the tables. And that means that there needs to be some kind of a type erasure. So a manifest log needs to be able to speak about like a table from any tree without caring about the type of the tree. But when we go to a specific tree, that tree needs to assert the sizes of stuff. So this is what this table tree info does. So table tree info is isomorphic to the table info here, except that it is parameterized by the specific type of a tree. So while here the tree ID is just a number, here the tree ID is actually encoded in the type of the thing itself. Okay, so so anyway, we kind of did this reverse downcasting, and then we insert this table into our in-memory structure of tables we have so far. And okay, and this brings us to the manifest level code, which I wanted to see from the start, and which is pretty simple. So we have our table. We find where we need to insert it in our sorted. Well, just okay. Okay, I'm just joking. Let's not try to pretend that I actually understand what this code is doing. Let's actually go and read it. Okay, so we want to insert this table. We insert it in the sorted array of keys so that we can sort its key into the sorted array of keys so we can quickly binary search the tables. And then we insert the table itself into the parallel array of tables, which is what we expect to do. Then, okay, we change the generation, which is about, changeable nature of persistent preset data structure, but let's not cover it today. Yeah, then we update the keys which are covered by this table, and this is actually important. So you see that, for example, in the table where we were manifest log. You see that like in the table we store k-mean, k-max, and in the whole level we store k-mean, k-max. This is for optimization. This is so that we can quickly rule out that a particular key does not belong to a table because it is like way too low, way too high. And then, oh yeah, right. I was confused by this chunk of code, but this is just some extra verification that after we have inserted the table, we could actually correctly find it. Okay, so coming back to our manifest log, open. So we read the block. If we figured out that this is a table which we actually do need to insert, so this table wasn't shadowed by any previous removal, we, after a bunch of interactions, call this insert table function to actually insert this table into the in-memory data structure, which stores all the tables. And we do this for every table inside our block. And then we should go to the next block. That's exactly what we do. We ask, okay, so now that we have dealt with this block, what is the previous block, which again, as a reminder, is stored as a pair of arrows and checksums at the header of the current block. And then we go and recursively read this thing again. But this is a curious thing. You see, like this previous returns null when we reach the null pointer. But here we have some extra condition to end earlier. So under some circumstances, actually, it seems that it is possible that we are not reading the entire manifest log, which is like, okay, what's happening here? And I guess as we are nearing the hour, I will probably leave it at that. And I'll leave it as a cliffhanger and as a quiz for the next episode at 5 p.m. UTC live on Twitch next Thursday, why it might be useful to ignore some previous events in the manifest log and say that, okay, we like doing only up to particular log block. Okay, but I think that's actually pretty good way to finish this episode. So again, the grand arc. Changeable. Changeable as a database consists of two principal parts. One is three principal parts. One part is consensus, the part where we exchange messages between networked replicas so that they agree on a particular sequence of events which guarantees strict serializability. The other part is state machine, in particular double entry accounting, the actual business logic that process all the incoming events, all the incoming financial transfers according to the logic of double entry bookkeeping. And finally, there is the storage, the part which is responsible for durably persistent data on disk. We've been looking at the storage. We've, I think, more or less fully covered the static picture of how the storage looks like. We kind of like said, okay, there is grid, then there is table. Table contains of index block of the data blocks. Index block points to the data blocks. And that's what we stored on disk. What we store in memory is the index of all the tables. So while we don't store in memory a pointer to every data block, we do store a pointer to every index block. And those stored are in these manifest data structures. The manifest is kind of like implicitly stored on the hard drive in the form of a manifest log. So rather than serializing the actual manifest, the actual set of levels and tables, we rather serialize this sequence of operations that, when done in order, actually produce the given manifest. So, and specifically, the sequence contains atomic operations. Remove this table to this level and add, remove this table from this level and add this table to this level, where this table is actually just a pointer to the table's index block, which is a pair of a 64-bit address and 128-bit checksum. So, and this log of events is exactly what we've been looking at today. It's stored as a linked list of blocks on disk. And when we open the data file, when we start our target, we read these log of events from the newest events to the oldest events and only keep the tables which are alive at a given point in time. And while we didn't actually get to actually changing the data on the disk, you already kind of like see that we are making a short steps towards this. In particular, this log of events supports add table and remove table operation. So you could imagine that the way we evolve our data structure is actually by adding this add table and remove table operations to our log of events. Okay, I guess that's all I wanted to cover. As quite unusual, we managed to end 2 minutes earlier this day, but that's actually good. That means that we managed to cover a well-contained chunk of target. Okay, thanks for watching, and would be glad to see you all again next week live on Twitch. And if you miss the live episode on Twitch, then there is always a recording on YouTube. Thanks again, and goodbye.